SwayamPrabha. Digital India. Educated India.
So now there are important things in Hill 1948 yield function. What are they? Anomalous behavior. What is that? So if we say that if R is equal to 1, less than 1, let us say, in general using the Hill 1948 yield function, you will see that the yield locus predicted by Hill 1948 yield criterion is located inside von Mises locus. Suppose R is equal to 1, if you say sigma 1, sigma 2, and if R is equal to 1, okay, then if R is less than 1, your yield locus given by Hill 1948 is inside this, something like this, okay. And if R greater than 1, yield locus would be outside, it goes out like this. That is what is generally observed by Hill 1948 yield function. But later on, Woodthorpe and Pierce, these two scientists, what they noticed is some materials, particularly aluminum alloys, have yield locus outside von Mises, though R value is less than 1. Suppose if you pick up R is less than 1, instead of locating inside the von Mises yield locus, it was outside von Mises yield locus, which is what with this peculiar behavior was unable to be explained by Hill's 1948 yield function, and that behavior is called as anomalous behavior. It is generally called as anomalous behavior first order. But there is some anomaly, okay, with respect to that material. Why? Because it is not following this particular requirement, one of the requirement. Okay, that if R is less than 1, which is what is seen in many aluminum alloys, okay, your yield locus is going to be outside the von Mises equation. Okay, this peculiar behavior was not explained by Hill 1948, so we are going to call that as anomalous behavior of first order. This can also be defined in this way. Okay, in this equation which we derived before, just now, no, for normal anisotropy, if you put the equibiaxial tension, sigma 1 equal to sigma 2 equal to sigma b, where sigma b is the equibiaxial yield stress. Okay, you are pulling the material in two directions equally, like alpha is equal to 1. This will give you alpha is equal to 1, let us say. Okay, alpha is equal to 1, no? Then there will be one yield strength, no? That is sigma b. If you put this condition in the previous equation, you will get sigma b by sigma ys equal to square root of 1 plus r by 2. 1 plus r by 2. So in this equation, if you see, if r is greater than 1, then sigma b would be greater than yield strength. If r is less than 1, let us say 0.5, then let us say this 0.5 means 1.5 to 0.75 square root, let us say, then sigma b would be less than sigma ys. Okay, but if sigma b is less than 1, this may not be satisfactory, okay, when we looked into this particular cases defined by this anomalous behavior. Okay, so this is the first anomaly that they found out. So now just a quick note of how do you find sigma b. Sigma b means what? Sigma b is means it's a yield strength in equibiaxial tension. That means this is your sheet, you have to pull this sheet equally in the plane direction, and you have to monitor its deformation to get the yield strength. So there are machines that can apply tensile loads in two directions at the same time, and these machines are meant for balanced biaxial tension test. That means you have to maintain alpha is equal to 1, let us say. So balanced biaxial tension, let us say sigma b, at which yielding occurs, is called yield strength in balanced biaxial tensile test, tension test. Therefore, sigma b can be estimated from these machines. However, it is not so easy, it is difficult. So you need to have a machine where you hold it and pull it. All the sensors have to be properly designed to monitor the deformation, load requirement, all those things. It is difficult. So instead of that, what can be done, it is generally like, assume that the sheet is subjected to compressive stress, let us say sigma c, the thickness direction. For example, like this. So you have the same sheet element, let us say you are compressing it with the sigma c. This will produce same effect as that of applying tension in two directions simultaneously as depicted below. Instead of pulling equally in this directions, which is mentioned here, what you do is you compress it in this direction. You provide C perpendicular to the slide instead of pulling it in the in-plane direction. So, when you compress it, it will anyway expand, which is what equiaxial tension is going to do. So, then we have to see how accurate it is, but then therefore, sigma B can be equated to sigma C, but sigma C is in the thickness direction. Okay, your sigmas, you have to compress basically sheet, the thickness direction, that is all. Okay. And we can say that this previous equation, no? Your sigma B by sigma ys we wrote equal to square root of 1 plus r by 2. This fellow can be replaced by sigma C. This fellow can be replaced by sigma C here, which is what I have written, sigma C by sigma y is equal to square root of 1 plus r by 2. So, many times, if it is difficult for us to do sigma, get sigma B, sigma C can be obtained in this way. Okay, so let us complete this part. What are the major demerits of Hill's 1948 Hill criterion? The first one is, it cannot address anomalous behavior of first order, which we have just now discussed, which means for r less than 1, sigma B greater than sigma ys were observed. Just now we discussed. There is one more thing which is called anomalous behavior second order, also we discussed before. You remember this equation? This we derived, no? This particular one. Sigma 0 by sigma 90 equal to square root of r0 into 1 plus r90 divided by r90 into 1 plus r0, no? Now, we also said that if r0 is greater than r90, then sigma 0 is greater than sigma 90, but some materials do not agree with this. This is actually called as another anomalous behavior. Okay, so this equation, no, which you already derived, what will happen if r0 by r90 is greater than 1, but some materials will show sigma 0 by sigma 90 less than 1. Okay. So, that is one problem with Hill 1948. Moreover, generally the criterion is applicable to sheet material which has got only 2 or 4 years during deep drawing. So, like we said, deep drawing, cup deep drawing earring is formed. So, only 2 or 4 years will be formed, not formed. The deep drawing behavior can be predicted accurately using this yield function which has got 2 or 4 years during deformation. Okay, but practically you will speak, there will be more years that can form. So, which cannot be addressed by Hill 1948. And moreover, it is also said that in axial tension test, the variation of yield strength with the direction is poorly predicted by this criterion, though the variation of R value is described better. Suppose you do tensile test and get R0, R90, and you also get sigma 0, sigma 90, and it is said that the variation of yield strength with the direction is poorly obtained. But R0, R45 prediction is, R value prediction is acceptable. So, these are the major demerits of this criterion. Specifically, the first two are very important, these two anomalous behavior. Now, before we go to next yield function, I thought this particular small derivation is going to be useful for us. How do you relate stress ratio and strain ratio for an anisotropic sheet or sheet in which we are going to include anisotropy while modeling? Okay. And of course, when you say that, the relationship is going to change between alpha and beta depending on the yield function you choose, and at least let us choose Hill's 1948 yield function. And how do you get alpha as a function of beta or beta as a function of alpha is what we will see here. So, we know this particular equation is known to us, no? We derived the following relationship between alpha and beta considering sheet to be isotropic. Using Levi-Masser's equation, we already derived it. We can look into it. And using this only we solved a lot of problems, correct? Alpha is equal to 2 beta plus 1 divided by 2 plus beta, and beta is equal to 2 alpha minus 1 divided by 2 minus alpha, right? So, we derived this equation before. So, now for Hill 1948 yield function in principal coordinate system, we derived these three just now, d epsilon 1, 2 and 3. We are going to use it. How? What is beta here? Beta is nothing but strain ratio, epsilon 2 by epsilon 1, right? So, this divided by this. So, 2 d lambda 2 lambda will go off. So, f into 2 minus 3 minus h into 1 minus 2 divided by g into 1 minus 3 and 1 minus 2. Fair enough. Now, how are we going to write it here? For plane stress, this fellow goes, this fellow will go off, right? So, f into sigma 2 minus h into this, g into sigma 1 plus h into this. Okay. So, now I am going to divide it by sigma 1 so that I get alpha, right? So, sigma 2 by sigma 1, alpha into f minus h into this becomes 1, this becomes alpha G into 1 plus H into 1 minus alpha. So, now we have derived it already. Now, only thing is we have to replace it with plastic strain ratios, which we going to use it. Okay, F is nothing but R0, so replace it with R0. H is nothing but R0 R90, replace it. G is nothing but R90, replace it. This fellow is R0 R90. So, finally, you will get this simple equation. Beta is nothing but alpha R0 minus R0 R90 into 1 minus alpha divided by R90 plus R0 R90 into 1 minus alpha. Right, very simple equation. Okay. Now, if you consider normal anisotropy, just before we discussed where R0 is equal to R90 equal to R. So, here if you in this equation, if you put R0 equal to R90 equal to R. So, it becomes a further simple case, alpha into R alpha minus R square into 1 minus alpha divided by R plus R square into 1 minus alpha, you will get, and then you simplify it, you get a simple equation here. So, using Hill 1948 yield function, of course, plane stress has to be there because we have to bring in alpha and beta, and if it is not the case of normal anisotropy, then this is the simple equation you have, you can relate it, and you put a case here, R0 R90 will be equal to R, then you get this particular equation. In this equation, if you put R equal to 1, what will happen to beta? Because it is an isotropic case now. R is equal to 1 means alpha minus 1 plus alpha, correct, divided by 1 plus 1 minus alpha. So, this is 2 alpha minus 1 divided by 2 minus alpha, which is what we got before, I think, isn't it? 2 alpha minus 1 divided by 2 minus alpha we got here, right. So, now depending on R value, you see the relationship between beta and R are actually changing. Until now we were assuming that R is equal to 1, then it was simple. Now, all our calculations, whatever we have done in the same problem is going to change by looking at one R value. Okay. Suppose if you take R is equal to, let us say, any R value you can take, maybe 1.5, then depending on alpha, the beta evaluation is going to be different. Okay. So, now you can see for anisotropic sheets by considering this particular formula, what will be the alpha beta for uniaxial, plane strain, pure shear, okay, and other two cases, balanced biaxial stretching, all these cases we can find out. Anyway, so now 1948 is over. Now, let us go to Hill 1979. We will not discuss much in all these things, we will quickly go ahead. So, Hill has proposed another yield function, Hill 1979, which does not exhibit the anomalous behavior first order mentioned before. Okay. The anomalous behavior first order which we mentioned before, no, that means though R is less than 1, your yield locus is going to be outside 1 minus yield locus, no, for like aluminum alloys. Then to avoid that particular problem, then he proposed another yield function which is given here, a little bit complex, but values are simple. F sigma 2 minus sigma m power m, G, then 3 minus 1 m, H 1 2 m, then you have A, B, C comes into picture, that will be equal to sigma naught power m. Okay, so now one advantage here is only principal stresses are allowed here, where sigma I are principal stresses, and F, G, H, A, B, C are, for example, anisotropic coefficients, and sigma naught as usual is uniaxial yield stress. This is a modification Hill has done, and here there is one fellow called m. This m is generally greater than 1. M has to be generally greater than 1, and what value actually depends on the crystal structure of the material. Let us say crystal structure, you remember BCC, HCP, FCC, depending on that crystal structure, this m value is going to change, okay, and is generally greater than 1. Sometimes people do some optimization to get this value for a particular material. What are these characteristics? You can see in this criterion, it is assumed that principal direction of stress tensor coincide with the principal direction of anisotropy, which means the principal coordinate system only we have returned. Therefore, the criterion does not include shear stress terms, which is obvious from this equation. So, it is restricted to loading along principal axis. This is what I was telling you. Moreover, it is also observed, I have not included any data in this, but it is seen that the criterion does not always satisfy convexity condition, which is a requirement for any yield function. So, convexity condition, we remember that convexity and normality we discussed, two important ones. So, your yield locus have to be convex at every point in the yield locus, right. So, that condition is not satisfied by this criterion sometimes. That is what is said. This is two important characteristics of this particular yield function. So, some cases we quickly discuss. Of course, you can do this exercise. I am not going to explain you, this is very obvious and self-explanatory, but this will lead to one important result. There are actually 5 special cases of Hill 1948 function under plane stress. So, which means that directly you can write sigma 3 is going to be equal to 0. So, if you substitute these conditions, okay, belonging to case 1, 2, 3, 4, 5 into this equation, you will get some other forms of equation, which is what is described here. So, case 1, if I take A equal to B equal to H equal to 0 and F equal to G, if you put in this condition, you will get this. Similarly, you can take case 2, you can try it and check. Similarly, you can take case 3, similarly you can take case 4, and similarly you can take case 5. So, basically the FGH and ABC, if you put some conditions to it, it will lead to 5 different cases. And the important one, it is said that this 5th case, A equal to B equal to F equal to G equal to 0 and F equal to G. If you put it in this equation, sigma 3 will anyway go off, this fellow goes off, no? Sigma 3 will anyway go off. A, B, F, G are 0. This fellow goes off, G goes off, A also fully goes, B also fully goes, okay, and F equal to G. Okay, so then you will get this particular equation. Okay, so F equal to G means, where is G for me here? G is here. Okay, G is here, no? So this is going to become F. So F sigma 1 power m, okay, then sigma 2 power m, then H into sigma 1 minus 2 power m, and sigma equal to sigma 0 power m. Okay, and this is what is generally called as Horsford yield function. So this Horsford, one form of Horsford yield function, this Horsford yield function is actually a case of Hill 1979 yield function. Okay, this Hill 19 yield function has got this particular characteristics. It has got some restriction also, which will lead to Hill 1990 yield function. This is just a general one I am describing. We are not going to discuss much. There is one more yield function called Hill 1990, which is little bit complex, and you can understand that here there is only one small difference here, that you have got T tau y. Tau y is nothing but yield stress in pure shear, sigma 1 equal to minus sigma 2, let us say, that also comes into picture, and A and B are material constants. M has got usual definition like what you have discussed in the previous one. So we are not going to discuss much here. Only thing we should know that this type of yield function exists, and sigma B is again available here. Okay, fine. Let us go to next one. This condition, this criterion is very important for us. 1993. Hill's yield criteria described before generally shows the condition sigma 0 is equal to sigma 90 enforcing R is equal to R 90, okay, which you can check it by this particular equation, correct, which we already done. This equation is actually in connection with your anomalous behavior, second one. Okay, this is what is being said actually. However, some materials such as aluminum alloy and brass sheets, they show almost equal yield stress. Okay, they show almost equal yield stress, but then R values are very different. But their R values along rolling and transverse direction, no, 0 degrees along rolling direction, 90 is along, they are very different, 90 degrees along different. So some of the example you can see I have taken. Suppose this brass 70-30 sheet, but this particular alloy you take it. Your sigma 0 126, sigma 90 is 125. They are almost same. But you see R0, R90 they are very different, which is actually breaking this particular requirement. It is actually breaking this particular requirement provided by this particular equation. Similarly, this particular alloy, if you take sigma 0, sigma 90 are almost same, but R0, R90 are relatively different. These two examples show that, okay, we need to be careful using your Hill 1948 yield function for some materials like this, because this particular equation enforces these two conditions have to be there, which is not the case in such materials. This is referred as anomalous behavior second order. So, now the question comes, how Hill 1993 is providing. What is it providing? So, in order to address the above concern, Hill 1993 yield criterion was proposed, which has a generality of Hill 1979. Why? Because in Hill 1979 it is addressing anomalous behavior number 1, which is what is said. At the same time, this Hill 1993 also should address anomalous behavior 2. Okay. So, with that, Hill 1993 was first proposed in the biaxial tension zone. Biaxial tension zone means the first quadrant of your yield locus. First quadrant of yield locus means this quadrant. Sigma 1 you can take sigma 2 now, this quadrant, first quadrant of where the biaxial tension comes into picture. No? Then this particular equation was proposed. Okay, you can just look into this equation. Okay, so of course you know that what is sigma 1, sigma 2, sigma 0, sigma 90, all are known to us except 3 things. One is C, then P and then Q. These 3 are a bit different. And what is C? C is also given here. C is actually a function of sigma 0, sigma 90, which are nothing but yield strength in 0 degree and 90 degree with respect to rolling directions. It is defined now. Okay, if you know sigma 0, sigma 90, you can get C. C can be substituted here, but you need to know P and Q. So, this equation actually can be satisfactory in 2 cases. That is what is actually I have shown here. Suppose you take a uniaxial tension case. Okay, suppose like you take along a rolling direction, you take one yield strength, let us say sigma naught. Since it is uniaxial, sigma 2 becomes 0. Fine. So, you put this condition in this equation and check, the left hand side would be equal to right hand side. Okay, because sigma 2 becomes 0, no? Then this entire thing would be 0. This fellow also will become 0. Sigma 2 0 means this fellow also will become 0. So, then what will happen is sigma 1 equal to sigma naught. So, these two will be equal because here it is 1. So, it is satisfied. Similarly, you can also get, so when you take a transverse direction, so when you call that yield strength as sigma 90 and you put sigma 1 is equal to 0 here, similarly left side and right side would be equal. So, thus the criterion is satisfied identically when the state of stress is uniaxial. So, when you pick up uniaxial type of deformation, this equation is satisfactory. You can also get, if it is biaxial, sigma 1 equal to sigma 2 equal to sigma b, you put it in this equation, okay, you can find out that it is going to give you this result, which is what we have written it here also. It is going to give you the same result. Okay, so you put sigma 2 1 equal to sigma 2 equal to sigma b in this equation. I think you do the small exercise. Okay, so you will get this particular equation. Sigma 1 is replaced by b. B square will come. B square will come. That's all. So sigma b, b square, sigma b square will come. So if you simplify this, you should get this particular equation, which also was shown before here for C. This has been satisfied. So it is suggested that the equation is same as the equation provided in the previous slide. This indicates that the criterion is satisfied identically in the balanced biaxial or equibiaxial mode also. Okay. So now what is P and Q? That is what we are going to discuss, and then we stop here about this particular discussion. So now, as I told you before, this yield function has 5 different fellows. One is your sigma 0, sigma 90, sigma b, and then P and Q. Okay. I said C, P and Q, but C depends on sigma 0, sigma 90 and sigma b. So I am writing sigma 0, sigma 90, sigma b, P and Q are there, okay, with respect to this equation, right. So this P and Q can be evaluated. So there is a big derivation available for this. So I am not deriving it here. So I mentioned very clearly not derived, refer some reference book. So please refer some reference book. So I have also indicated a reference book here, look into it, and then finally you will see that you will get the simple P and Q equation, which are actually functions of already known values R0 and R90. So we are going to just see the end result here. If this is the yield function, okay, and one of that is C, which is already known, so then this yield function is easy to use. Why? Because all the properties are available with us. Sigma 0 can be obtained, sigma 90 can be obtained, sigma B also can be obtained. Now P and Q you have to evaluate. Again, P and Q equations are also available for us, in which only unknown things are actually R0 or 90, which also can be obtained. Okay. So now finally we can say that in order to use yield 1993 yield function, only 5 properties are required: sigma 0, sigma 90, sigma B, which are already there. Now P and Q, instead of that you need to get R0 or 90, which are easily available. How do you get? You can do tensile test, you can do R value test, and you can do equibiaxial tension test. Equibiaxial tension test. So you plug in all these things into this equation. This equation can be used to model any deformation process. So now this is the case only if you have in biaxial. This is how it is derived now. So now you want to expand or extrapolate this for other locations, 1, 2, 3. These 3 zones in the yield locus. There is a small modification that is allowed here. I have marked it in red color. That small change is only there. Otherwise, everything remains same. So sigma 1 becomes mod sigma 1, sigma 2 becomes mod sigma 2, and you can extend it to get other quadrants. The above yield function suitable for first quadrant can be extrapolated to other quadrants by using this generalized function. Okay. So I think with this Hill 1993, it is said that it can address the anomalous behavior number 1 and number 2. That is what is said, and that is one of the merit of this one. Both first order and second order anomalous behavior are addressed here. It depends on only 5 material properties just now we have seen, right? Sigma 0, sigma 90, R0, R90 and sigma B, which can be evaluated easily. What are the demerits? Useful only if directions of principal stresses coincide with orthotropic axis. That is why you have only sigma 1, sigma 2, okay, right. It is also said that it does not allow variation of anisotropic coefficient uniaxial yield stress in the plane of the sheet. That is another demerit we say, but then we have to accept it and go ahead because it is satisfying the first 2 problems which faced by 1948. Okay. So before 1993, 1979 also can be used, but it can address only the first one, anomalous behavior first one, that is what is said. Okay. So but the second fellow addresses both. 1993 addresses both. Fine. So I am stopping here with respect to yield function discussion. So there are a lot of other yield functions. Okay, we have seen only Hill 1948, 79, 90 and 93. Hill 1948 has been described little elaborately. Okay, and other 3 cases are discussed minimally to what is actually required for us with respect to its characteristics and merits and demerits. So this particular table, I took it from this particular book. We redrew this particular table, and this particular table tells you different yield functions available plus what are all the data required if you want to use this yield function. For example, Hill's 1948 you need, as we discussed, you need sigma 0, then R0 R90. Sigma 0 or sigma 90, any one you need, R0 R90. 79 also we have seen, sigma 0, then of course sigma B was introduced, then R0 is required. Sigma 90, there are a lot of things required, you can look into that equation. 93 also we said only 5, no? Sigma 0, sigma 90, sigma B, R0, R90 are there. There are several other yield functions you can look into it. Okay, various yield functions, Hills 1979, Barla himself has 2-3 important yield functions. Okay, you can see that 1, 2, 3, 4 and KB is also there. Okay, there are 4 parameters in this, 6 parameters. So there are several such yield functions available which can predict the forming behavior accurately. Again, it is recommended, just a recommendation only, that Hill 1948 is a useful yield criteria to model forming of sheets and simple to implement because properties can be evaluated easily, but however, avoid using it for aluminum alloy forming. Okay, but for if it is aluminum alloy, then one can use 1990 or Barla's yield function, anyone, or KB's or others also, whatever is available, better suitable for modeling aluminum alloys. However, several material properties are required. So you have to be a little bit careful which one to use to predict what. Suppose you want to see the tube forming of aluminum alloy, you want to model it, then use one of this, the bottom ones, 1990 Barla's or something, but then there could be several parameters, material parameters you have to characterize. Okay, but it is generally written that it's to avoid it. But if it is a steel tube and you want to study its bending behavior, or sheet, you have to study its deep drawing behavior or any stamping behavior, HIL 1948 would be more than sufficient, okay, because the properties can be easily calculated. Okay. So, this is what we can discuss about anisotropic yield function. So, we have seen 4 important yield function, predominantly HIL 1948, and HIL 1948 also we rewrote that equation in few different forms. That is the main thing. Next one is important one is we using HIL 1948 yield function, we derived relationship between alpha and beta, which was earlier for us was a simple one without considering R value. This alpha beta had R value into that equation, which can be used for anisotropic sheets. That is the main thing. So, before we complete this, let us briefly discuss about the difference between isotropic hardening and kinematic hardening. What is it? Isotropic hardening was just introduced to you just now. It is the case in which yield surface or yield locus remains same shape but expands with the deformation or increase in stress. It is what is shown here for you. This is well known to you, sigma 1 versus sigma 2, yield locus. We always draw first yield locus, initial yield locus, and then subsequent yield locus when you deform the material. So, I have drawn here a red color line, you can see from here to here you can see it is elastic loading, and after that it is plastic deformation or strain hardening, and then you can unload the material. That is the way it is going to work. And for the yield function, if you want to define, which you already defined, the function is a, let us say, f minus k equal to 0 in the simple way you can write, which also tells the fact that the shape of yield locus is specified by initial yield function, that f, and size changes with respect to hardening parameter k. I hope you remember that we introduced this one when we discussed about at the end of von Mises yield function, where we are going to discuss about sigma bar. At that particular slide or lecture, you can see that we wrote a similar one, and then I was discussing with you that one part of the equation on the right hand side is going to decide the form of the yield equation, that's going to tell you the shape of the yield locus. On the left hand side, which is nothing but your, I think, 2 sigma bar square, which is equal to k, we wrote, I think that k was going to decide the size. Fine. So, now this equation is written. So, now what we are going to do is, this is also something new for us. Suppose if you want to write von Mises yield function, so how do you write? So, von Mises yield function at yield can be written in this fashion. So, f is equal to, this is known to you, right, 1 by square root of 2 into square root of 1 minus 2 the whole square, 2 minus 3 the whole square, and 3 minus 1 the whole square, minus y. Minus y. Y is nothing but, let us say, sigma 0 or sigma f, like that. We might have used sigma f, isn't it? So, now in this, if you put 3 is equal to 0, it will lead to von Mises equation we just now discussed. 4-5 slides back we discussed that. No? When we study a case of HIL's 1948, it resulted in von Mises yield locus, no? The same equation. This equation is well known to us, which is also equal to, we can write the same equation in 2 other forms. One is using J2, the other one is using deviatoric stress. Okay, square root of 3J2 minus y, y is a yield strength, which is also equal to square root of 3 by 2 into Sij minus y. This Sij is nothing. What is Sij? Sij is nothing but stress deviator tensor. This also we have seen in expanded form. When we derive von Mises equation, there is one particular stage where we derived that equation as a function of sigma ij dash, right? That is nothing but this Sij only. There we have used sigma 1 dash, 2 dash, 3 dash. Here we are just using Sij only, where Sij is nothing but deviatoric stress, but only difference is here we are writing in indical notation. This is index notation we are writing. There we wrote expanded form. So, how to expand it, one has to understand from a different book. We are not going to discuss here. Y is known to you. What is J2? J2 is a second invariant of deviatoric stress. Invariants, you know, there are invariants like I1, I2, I3 and J1, J2, J3. Okay. So, I1, I2, I3 are generally related to stress tensor, and J1, J2, J3 are related to deviatoric tensor, and J2 is the second invariant of deviatoric stress. That also can be written in this way. So, these are the different forms we use. These 2 forms are already known to us. Only this one is something new. I have written here, this also you should know that. Sigma bar is nothing but square root of 3 into J2, which is nothing but 3 by 2 into Sij, which is what you have written here. So, now with respect to the previous equation, what I am going to do is, I am going to just substitute this this function. Okay, this function is nothing but f is becoming now, this is the function, no? So I am going to use this square root of 3 into j2 minus y minus k equal to 0. Okay, this is how von Mises yield function can be written. Okay, so now isotropic hardening simply implies that if the yield strength in tension compression are initially the same, they remain equal even in further deformation with increase in plastic strain, which means Boschinger effect is not considered here. So I think we have also studied this in bending now spring back. If you take sigma versus epsilon, so you deform it like this and then you unload it and then you go this way, okay, you will see that there is no change in yield strength because of softening in the compression side. They remain equal. So which is what is a general assumption we are making here. So we are saying that if the yield strength in tension compression are initially the same, they remain same during the evolution also, which means you cannot define or model Boschinger effect with respect to this, which actually led to kinematic hardening. So what is that? To model Boschinger effect, where hardening in tension will lead to softening in compression, which means that in the compression side your yield strength will be less than what it was in the first cycle, in the tension side. Then if you want to include that, then we can do that by kinematic hardening. And kinematic hardening, if you want to describe with respect to yield locus, it will look like this. Again, blue one is the initial one and the red one is the current one because of kinematic hardening. So this is a elastic part and this is a plastic deformation part and then unloading part is written, and you will see here that the shape is same. Your yield locus actually gets translated in the stress space. The yield surface remains same shape and size, but translate in stress space. Okay, the shape and size remain same, but it gets translated, it moves in the stress space, which actually is a good one to model Boschinger effect. So how are we going to write it? We are going to write that yield function, any yield function you pick up, okay, with respect to kinematic hardening. If you want to write it, then you can write a function of sigma ij minus alpha ij equal to 0, where alpha ij is called as back stress or shift stress. Okay, so what do you mean by alpha ij? Alpha ij means it's a back stress or shift stress, which can be defined schematically like this. Okay, so let us say sigma 1, sigma 2 you are drawing. Let us say this is initial yield locus. Okay, so the locus is shifted by alpha ij. Locus is shifted by alpha ij relative to the stress space as shown in this figure. So you are going to shift the entire yield locus by alpha ij. Okay, that is what meaning of this particular equation. So now what are we going to do is very simple. We are going to rewrite this particular equation in this format. Now in this, what I am going to do is I am going to use this equation is okay. So I am going to use this known format for me, the Dietrich test, no? This particular form, square root of 3 by 2 into Sij minus y. No? Now what am I going to do is this Sij is a Dietrich test deviated tensor, no? And what am I going to do here is sigma ij minus alpha ij, right? You imagine that this alpha has got one Dietrich part, which I am going to remove from Sij, okay, which is what I have written here. By considering von Mises material, again von Mises is used, but kinematic hardening, okay, which is the simplest case. Von Mises isotropic hardening we have seen just before. Okay, von Mises kinematic hardening is what we are looking at here. Other yield function and then kinematic hardening is further complex. By considering von Mises material and using Dietrich part of sigma minus alpha, okay, Dietrich part of sigma minus alpha instead of Dietrich part of sigma. Okay, so I am going to write that 3 by 2 square root of 3 by 2 into, it was initially Sij minus y. Now I am going to write sigma 3 by 2 into Sij minus alpha ij into Sij minus alpha ij minus y equal to 0, where my this alpha d, no, this alpha d is nothing but a Dietrich part of alpha. Dietrich part of alpha. Since we are speaking about Dietrich stress, then pi plane, no, or Dietrich plane will come into picture. And what is it? It is what is given in this particular figure. In pi plane, or deviatric plane, we know what is it. Deviatric plane means on the deviatric plane, you know how one measure is going to be. It's going to be a circle, right, which we discussed long back. On the deviatric plane, your one measure is going to be a circle. In 3D, actually, it's a surface, it's a cylinder, right. So when you look on the deviatric plane, it will look like a circle. Okay. So now with respect to that, what is this S minus alpha d is going to tell? That's what is discussed in this particular figure. So in pi plane, the deviatric part of alpha, there is deviatric part of alpha, which is alpha d, let us say, denotes shift of one measure circle as shown in this figure. Okay, what happens? So this is your one measure circle. Okay, this is your one measure circle. Sigma 1 dash, 2 dash and 3 dash, you see this is a one measure circle. Okay, on the deviatric plane, pi plane we have given here. Now this circle is shifted here, okay, let us say by alpha d times, alpha d shift is seen here with on the pi plane, then S minus alpha d denotes this particular vector. If this is the S. What is S? S is nothing but Sij, which is a deviatric part. Alpha d is nothing but the deviatric part of backstress, and S minus alpha d is this, which is what is actually put here to define your kinematic hardening one measures material using one measures yield function. So it's very simple to tell 3 by 2 Sij minus y equal to 0, which is the conventional one measures yield function, is going to be modified as root of 3 by 2 into Sij minus alpha d, let us say, into Sij minus alpha d minus y equal to 0. So this part is the deviatric part of the backstress. That is what is written here. Of course, one can write it with respect to sigma ij also. That is another way people write. Okay, that is also possible. There is only one small thing that we are going to do now. What is that? We are going to see how this alpha is connected to your plastic strain increment or the direction of plastic strain increment. So this linear kinematic hardening model, it defines actually how yield surface is translated with respect to direction of strain increment. You can see that suppose this is a d alpha, okay, how is it actually connected to the direction of d epsilon p? Direction of d epsilon p is known. It is actually perpendicular to the normal drawn at any point in the yield locus, right. So in linear kinematic hardening model, we are introducing here the backstress assumed to depend on plastic strain following this particular equation. You can say that your alpha ij is equal to C into epsilon ijp. That means it is linearly related using C, where C is actually a material parameter and it is constant when you speak about linear kinematic hardening model. Okay. So what does that mean? It means that yield surface is translated in the same direction as that of plastic strain increment linear kinematic hardening model as shown in the schematic. If this is the direction perpendicular to it, your d alpha or alpha is going to be in the same direction. But if your C changes deformation, then you need a nonlinear kinematic model, which is not discussed here. You can go through it. Okay. So now if you want to replace alpha ij by C into epsilon ijp, we can do that in the previous equation and you can modify the kinematic hardening model. So thank you.